Okay, good morning. Let me try to start where I had left off. Remember, we were discussing generation of perturbations during inflation. And what we had considered was as follows. We were focusing on the scalar perturbations. I haven't come to vector and tensor perturbations. What we had was a metric of the following form. ds squared is equal to 1 minus 1 plus 2a dt squared. Remember, we have fixed the gauge. So there were only two scalar perturbations, dxi, dxj, psi, and a. And we had said a equal to psi equal to some capital phi, which we refer to as the Bardian potential. And we had arrived at the Bardian equation. In the presence of fluids, we had arrived at the Bardian equation. Okay, I don't recall whether I call as CS squared or CA squared. My notation changed from one set of notes to another. It's P dot by rho dot, whatever I had called. CA squared script H phi prime minus CA squared nabla squared phi, right? Plus 2H prime plus 1 plus 3 CS squared H phi equal to 4 pi GA squared delta PNA. And I presume you recall the definition of delta PNA. It is delta P minus CA squared delta. And CA squared is, of course, as I was just saying, P dot by rho dot. And we are focusing on situations where it was dominated by a single fluid. And what we had shown was the following. Right. On super Hubble scales, I'm just repeating, we are still not reached generation of perturbations. There I need to consider the source to be a scalar field. We are still considering fluids. I just want to emphasize, highlight a couple of points before we proceed further. Remember, on super Hubble scales, and when you have scale factor of the following form, trying to recall how I wrote the scale factor, when the scale factor is of the following form, is some a naught eta power beta plus 1, we had shown that phi k was of the following form. Phi k equal to beta plus 2 divided by 2 beta plus 3, right? C1 of k plus beta plus 1 by a naught squared, C2 of k divided by eta power 2 beta plus 3. This is what we had obtained. And we had also shown there was a quantity which we refer to as the curvature perturbation, which was conserved on super Hubble scales, right? Let me get that expression for the curvature perturbation, which was this, okay? Which was R equal to some psi plus H by rho plus P, delta Q. And you can again write the use the Einstein's equations, and remember psi equal to phi to finally write it in this following form. Plus 2 rho by script H phi plus phi prime divided by rho plus P. Now, what is interesting is that if you, and we had seen that R prime, or to be specifically RK prime in Fourier space, is roughly equal to 0 on super Hubble scales. Okay, on super Hubble scales. and when delta PNA is 0. This is what we had seen. Okay, this is again to emphasize in the case of fluids. Now, what you can do is that you can take the solution and substitute in this RK. All right. And interestingly, if this is power law solution, you can write this in terms of W. Right? You can relate beta to W. Okay. And therefore, when you do all that, what you find is the following. You can write R in terms of W. I need to pull out another notes. Okay. So what you find is the following. I'm going to erase this. I'm going to keep that title for a few minutes. Okay. I will need this equation. I will have to write it again. Okay. And what you essentially find is that you can write phi k as follows. Okay. I'm going to call this as CG of k. The reason will become clear. 3W plus 1 divided by 3W plus 5. What I'm trying to say is that when you have power law expansion of this form, it corresponds to a constant W. You can establish this. And you can obtain a relation between beta and W. Okay. And that's all I have done. Okay. And 2 gamma plus 3 plus CD of k, 2 by 3W plus 1. Okay. Divided by, okay. Some constants, I pull it out. Okay. I write this as eta power 2 gamma plus 3, 2 beta plus 3. And I mentioned that this is the decaying mode. At large eta, this is going down with time, which means at very early times, it is large and it is not. Such initial conditions are not possible. And I was arguing towards the end of yesterday's talk as to how on super Hubble scales, you expect the curvature perturbation generated during inflation to be a constant. So what we are expecting is that, so I will finish one more step and make a few more remarks. So I can take this phi and plug this in here, right? And you obtain RK to be the following. 3W plus 5. Let me write it a little below. Okay. IK, right? And if you plug this in, this is nothing like CG, nothing but CG of K. All right. It is this CG of K that is conserved on super Hubble scales, right? RK is conserved and CG of K is what I need to predict from inflation, from my initial conditions during inflation. And the subscript G denotes the growing mode. It's not growing, it's a constant. And what is interesting is as follows, okay? I'll squeeze in and write a couple of expressions here, okay? You can show that during radiation, phi kr is 2 by 3 Cg of k. I'm going to, okay, Cg of k. And during, this is, did I say inflation? I'm sorry. This is radiation domination. Radiation domination. During matter domination, all you need to do is substitute W equal to 1/3 and 0. This happens to be 3 by 5 Cg of k. Okay. And what you can show from this is that phi k during matter domination is what? How do I relate it to? It is phi by 3, okay? Phi by 3 Cg of k, right? But that is phi by 3 times Cg of k is 3 by 2. No, there is something. No, there is Cg, phi by 3 Cg. Okay, phi k during matter domination is transition to matter domination. It is phi by 3 Cg of k, and Cg of k is 3 by 2. Okay, I'm sorry, what is it? Right. Okay, so let me write it slightly differently. Now, if I write Cg of k as in terms of radiation domination, I will get Cg of k is 3 by 2. I'm getting it the other way around. 5k md is, no, I have, okay. This is 3 by 5. I don't know what, okay. 3 by 5, okay. And then what is it? It is 3 by 2. 3 by 2 into 3 by 2. Sorry, 3 by 5 into 3 by 2. I just made that error. 5k of radiation domination. And this is 9 by 10. This is the famous result that you may have heard of, that from very early times to late times, on super Hubble scales, the Bodin potential changes by a factor of 5 by 10. Now, what we have done, I hope you recognize, is that the phi changes. It is constant on super Hubble scales, the phi subscript k, but it changes from radiation domination to matter domination. Cgk is fixed quantity. It's provided by a primordial perturbation, but it's a different constant from matter domination to radiation domination and matter domination. And we are able to relate that using the fact that R is conserved. Okay, R is conserved, and using that we can relate. We can show that, let us say at the end of inflation, you have a 5k on super Hubble scales, deep inside, matter domination, but on super Hubble scales, the largest mode just is almost a constant. Phi is almost a constant. It changes by a factor of 9 by 10. And that is a result I wanted to highlight before I come back to the case of generation of perturbations. So where do we start? We go back to my Bodin potential. I'm going to erase this part. And I'm going to retime this definition of R. Erase this. Right. Just get me back. Get different set of notes. Just bear with me. Right. So what do we have? We had arrived at the Bodin equation, a version of the Bodin equation. And now we are talking about generation of perturbations during inflation. The delta G mu nu is sourced by the scalar field, single canonical scalar field. And we had, just as in the earlier case, we can arrive at, by combining the 0, 0 or TT and the IJ with I equal to J rather, equation, you can arrive at the Bodin equation. There is only one function that you are interested in. Notice the perturbations in the metric are described by capital phi. And the perturbations of the scalar field are described by delta phi. But there is a set of Einstein's equations relating them. So essentially, you reduce to one function, okay, namely the evolution of phi, okay? And you can arrive at the equation. I'm repeating this. We had written this yesterday, 3h into 1 plus CA squared phi prime, okay, plus 2 script h prime plus 1 plus 3 CA squared h squared, okay, into phi, correct? Sorry, just give me a minute. Right, minus CA squared into nabla squared phi equal to 1 minus CA squared nabla squared phi. Okay, which essentially implies that delta PNA for the case of scalar fields is given by this expression 1 minus CA squared 4 pi GA squared del squared phi. Okay, and this was R, okay? And therefore, essentially what happens is that, all right, R prime, okay, R prime, I can arrive at, we had already arrived at an expression for R prime. If you look at your notes, if I had a fluid on we had obtained an expression, not on superable scales, it's an exact result, okay, where R prime equal to a linear combination of nabla squared phi and delta PNA. But here we find that delta PNA for the case of scalar field is proportional to nabla squared phi, and therefore what you have is a simple expression for R prime, which is essentially given by this expression, R prime equal to script h by h squared minus h prime nabla squared phi. Okay? Or if you write in Fourier space, oops, R k prime equal to minus h by script h squared minus h prime k squared phi k. Okay? Now, in the small k limit, I have been saying what refers to the super Hubble and the sub Hubble limits as small k and large k. Small k corresponds to large wavelengths, and therefore the super Hubble limit, and large k will correspond to sub Hubble limit. Of course, I'm taking blind limits, extreme limits. You have to actually compare two quantities to say whether it is sub or super, okay? And I will talk about how to compare them. Well, until now, whatever I've been saying, essentially when I say sub Hubble, right? Super Hubble is what I have been talking about, super Hubble. This corresponds to essentially K being much, much smaller than AH, okay? Or, K by A is much, much smaller than H. Or in other words, what I had called as lambda physical earlier, okay, which was proportional to A, this is much, much greater than DH. Remember what was DH? DH was H inverse, okay? And similarly, the sub-Hubble limit will correspond to the other limit, okay? K by A is much, much greater than H, or lambda P is much, much smaller than DH, okay? So in other words, this corresponds to K much smaller than AH and K much greater than AH. And what happens is that in this limit, where this is negligible, RK prime is nearly zero. Earlier, when I talked about background evolution, I had said, we had worked in the slow roll approximation, and we had seen how, I have mentioned, I had asked you to solve for the background numerically, and I had urged you to compare the exact numerical solution with a solution in the slow roll approximation. And I had mentioned how it's a remarkably good approximation. And what you will find is that, on super Hubble scales, this indeed comes down to zero very quickly. RK prime comes down to zero very quickly. In fact, RK prime decays like e power minus 2n, okay, on super Hubble scales. So it quickly decays, and therefore the moment it leaves the Hubble radius, within a few e-folds, the amplitude of these modes freeze. I will talk about it further. So let us summarize. What have we done? We had compared the equation for the Bardian potential with the source being that of a scalar field, with the original Bardian equation in the case of fluids that we had obtained. And we had determined that delta PNA is proportional to nabla squared phi. And I took that expression for delta PNA and substituted in that expression for R prime that I had obtained, okay? And for the case of scalar fields, what you obtain is this result, okay? And, what essentially it implies is that RK prime is nearly zero on super Hubble scales in the case of single field models. This is largely true unless in some exceptional cases where something strange happens at late times during inflation. But in most of the models of your interest, slow roll inflation and so on, RK prime is indeed, remarkably good constant on super Hubble scales. Now, what we needed to do was as follows. We had this definition for the Bardian potential, for the curvature perturbation. What you need to do is you take this differential, okay, and then use the Bardeen equation, all right, to arrive at an equation of motion describing this quantity, which we refer to as the curvature perturbation. So remember, I had written down the metric, right? The metric, the spatial part of the metric in the gauge I worked with, okay, had contained what was the perturbation that appeared in the metric? The psi, okay? Remember, A and psi were dependent on space and time. Those are describe the inhomogeneities. And, what you find is as follows. Remember, again, on super Hubble scales, R is like phi, okay? And what you find is that given that metric, you can calculate 3R, okay? I think if I recall correct, what is 3R? The curvature on a constant time surface, okay? And that, if I recall correctly, modulo constants is proportional to nabla squared phi k, okay? All right, nabla squared phi. You work in real space, okay? And in other words, what essentially this R is, it reflects the deviations from spatial flatness. Remember, the background was a spatially flat universe. Now there are perturbations present, okay? And if you calculate the 3R, I forgot the constants, maybe, there will be factors of 6 and a 1 over a squared possibly, and so on, okay? But the bottom line is that the 3R is of the structure, okay? And in some sense, phi or equivalently R reflects the deviation from spatial flatness. And for this reason, this R is often referred to as the curvature perturbation. Now, the exercise I had given for you is to differentiate this, use this Bardeen equation, okay, and to arrive at the equation of motion governing the curvature perturbation. And I had written this equation down yesterday, and I'm going to just write that equation, okay? It happens to be R double prime plus 2 Z prime by Z R, okay? We are going to work in Fourier space plus RK prime plus K square RK equals 0. Okay? And what is Z? Z is some convenient quantity which we define. It's often referred to as the pump field or so, and it's given by this expression. Okay? So where is the model of inflation buried? It's buried in Z. I hope you recognize. If you give me a V of phi, you recall the Friedmann equations. Okay? We had, by mixing the Friedmann equation suitably, we had written phi and V in terms of some quantities involving H and H dot, if you recall. What essentially it means is that there is a function A of t, okay, which is determined by a V of phi. They are equivalent. If you specify one, you specify the other. So if you specify V of phi, essentially I can obtain A, phi dot, and H. So that determines Z, all right? And once you give Z, you substitute in that expression and solve for it, okay? And solve for that. The question is, what kind of initial conditions are you going to impose? This is what I was discussing at the very end of the talk yesterday. So what do you have? We define something called, I have already said, this is the curvature perturbation. You define something called the Mukhanov-Sasaki variable. Right? Vk is Rk times Z, okay? Rk is Vk divided by Z. Okay, all right. Now, if you substitute this here, either way, this way or that way, what you obtain is the Mukhanov-Sasaki equation. Okay, all right. Our goal is to satisfy, is to solve this equation with some initial conditions. What one does is that, remember, we've been saying that the perturbations are generated through quantum fluctuations. So what you actually do is as follows. you quantize either Vk or Rk, okay? R eta comma x is written, it's an operator. It's usually written as d3k by 2 pi power 3 by 2, right? And then you write it as some ak r. Okay, I'm going to write this as fk eta, okay, e power ik dot x, right, plus ak dagger fk star of eta e power minus ik dot x. This ensures that the R, curvature perturbation, is a real quantity. I've just elevated what's a classical quantity to a quantum operator. That's what you do in quantum field theory. You have a classical field, you raise it to a quantum operator. Remember, if you had a scalar field, remember a simple massless scalar field in a Minkowski space-time, what you would have done? What would you have done? You would have written some phi of k, e t comma x, as integral d3k by 2 power 3 by 2 ak. You would have obtained the solutions, right? Okay, which will be e power minus I omega t here, and that's referred to as what is known as the positive frequency mode. Check out some text on quantum field theory, okay? And then this will be e power I omega t, okay? I'll come to you in a minute, just bear with me. What does that equation fk satisfy? I hope that is clear. That satisfies this equation, okay? I presume that is clear. Fk satisfies the same equation as Rk. And now you define a vacuum state, AK0 is equal to 0 for all k. Okay? In Minkowski spacetime, that will be the Minkowski vacuum. Okay? The vacuum that we'll define is here in the context of inflation is often referred to as the Bunch-Davies vacuum. Okay? And we will calculate the correlation. This is a, you know, this is a single, you know, this is just an operator. The 2-point function describing the curvature perturbation, right? Or the Fourier space version of it is what we will define as the power spectrum. Okay? So this, I hope you can see, can be written as some d3k by 2 pi 3 by, but these factors and all are conventions, some rk hat, okay, e power ik dot x. And you can quickly convince yourself that rk hat is what? Ak fk of eta plus a minus spectrum will be evaluated at late times during inflation. This is a good time to ask questions. There is a factor of 1 over. That is correct. That's correct. You will wait for me. It'll appear. It'll appear.
But why
doesn't appear? That is absorbed in FK.
Oh, okay.
Okay. I understand your concern. Firstly, you know, if you read your quantum field theory textbooks, you say that integral d3k by root EP is explicitly Lorentz invariant. Okay. And therefore you write that times e power minus I k mu x mu, which is a Lorentz invariant quantity. So I have written, decomposed the scalar field in terms of Lorentz invariant, explicitly Lorentz invariant expression. But I don't need to have Lorentz invariant. I'm not in Minkowski spacetime. So that is not a concern for me, the appearance of EP, but you will see that there will be some version of that which will appear, okay, because of the initial conditions that we will have. No, that's only in Minkowski spacetime. We are not in Minkowski spacetime. Is your Friedmann metric Lorentz invariant? It's not. So there is no Lorentz invariance. It's broken in general relativity. Yeah. There's a larger general covariance. But it's another issue, vacuum are not generally covariant and so on and so forth. We can speak privately about it, okay? But the concept, 2 points. One, something like a EP will appear, okay? You will see that when I write down the solution, okay? Because in the Minkowski limit, I will clarify this point, you expect such a solution to be present. Number two, actually, there is no Lorentz invariance here. We are in a Friedman universe. And while vacua that you define, in flat space-time or Lorentz invariant, vacua in general in quantum field theory in curved space-times are not general coordinate invariant. That's a different issue. So there is an issue of trying to define what is the vacuum state here, but that can be defined in an unambiguous manner, which I will clarify in a matter of minutes. Avi. Okay, take the microphone. Oh, there is no vector. This is K. That's what I'm saying. There is no minus. It's not a vector. It's K. It's just the magnitude. Okay. That's not surprising, right? The R, I haven't written a vector K here because there is only nabla squared, this only depends on K, not vector K. Yeah? All right. Okay.
We assume that there is a unique vacuum, but
I will clarify and I will let you judge whether it is unique. You will see that that's the best we can define in a time-dependent background. Any brief question? Any other brief question? Okay, all right. So what do we need to do? We need to solve this differential equation and impose some initial conditions. So I'm just going to erase this. And I can erase this now. So I'm going to define the power spectrum. Okay, I've already defined RK in Fourier space. Okay, the scalar power spectrum, which is what observations try to constrain, is defined through the following relation. RK eta RK prime eta, I hope I get this, it's 2 pi squared by K cube, I believe this is what it is, delta 3 K plus K prime PS of K. This is the definition of the scalar power spectrum. So you plug this in here, okay, and you can show that PS of K is K cube by 2 pi squared mod Fk squared or K cube by 2 pi squared mod Vk by Z squared. This is what it is. I will let you do that exercise. It's not difficult to do. Okay. Remember, AK and AK dagger satisfy the standard commutation relations. Okay. And you can easily establish this. Now, what we need to do is that, notice, there is a time dependence here. Okay. I should have explicitly maybe written this time dependence. And this time dependence arises. Okay. And when do we have to evaluate this power spectrum? Okay. Remember, I have drawn this picture earlier. So let me draw this picture again. This is the power spectrum. All right. Sorry. Inflation, radiation domination, right? Cosmologists want the power spectrum at re-entry, late time cosmologists. Okay. And we are going to evaluate the power spectrum at late times. Typically, it has to be evaluated at the end of inflation at this point. Remember what this is. DH, comma lambda P, and this is log E, which we'll refer to as number of E folds. Okay. And you need to evaluate at late times. But I have been repeatedly saying the following. What have I been saying? That very quickly after it leaves the Hubble radius, it becomes a constant. Okay. So essentially what you need to evaluate, you need to choose a eta, which is at sufficiently late times such that all the modes over which you are focusing on are well outside the Hubble radius. Okay. So, and That is the limit in which we will evaluate the power spectrum. In order to evaluate the power spectrum, now we need what do we need? We need a model of inflation. Okay, all right. So one model which we consider is power law. Okay, so is power law inflation. So power spectrum, or rather PS of K, the scalar power spectrum in power law inflation. We also need to consider tensors. I will come to that later. So what do I have? Remember this expression. I will just write it here on top. KQ by 2 pi square mod BK squared by Z squared. And it's clear that we need to evaluate the spectrum at late times. Okay. So what do I have? Z is A phi dot by H. I was mentioning towards the end of yesterday's lecture that phi dot in power law. Okay. So what is power law inflation? A is proportional to some T power Q. So what is H? H is proportional to 1 over T. Okay. And if you recall, phi went as log T. So phi dot goes as 1 over T. Right? So what does this become? In power law inflation, it is A, phi dot goes as 1 over T, H goes as 1 over T. So this is proportional to A. Okay. All right. So now what do we have? Remember my Mukhanov-Sasaki equation. So Vk double prime plus K square minus, it becomes A double prime by A, Vk equal to 0. Yeah. So now I need to look at my notes to make sure that I want to see how I have written. No, on the wrong file, just sorry. We had written it as eta power beta plus 1. Okay. All right. Just give me a minute. Right. So we had written as T power Q. All right. Now Z is this, and I can write A of eta as follows. To be precise, I will write this as some A2, which is a constant, some minus H1 of eta, beta plus 1. All right. And I will let you convince yourself that beta is 2Q minus 1 by 1 minus Q. Okay. All right. You can check some cases. Q equal to 1 is radiation, right? Sorry, Q equal to half is radiation, right? That's correct. So this is beta is 0, A is proportional to eta. Okay. And d zeta is beta equal to minus 2. Okay. And that corresponds to Q tending to infinity. If Q tending to infinity, this goes to minus 2. Okay. Right. It's 2Q by minus Q. Okay. Why is Q tending to infinity? When Q tends to infinity, that power is exponential. Okay. It goes as 1 over eta. I will let you check all those expressions. Now, what do I have? I need to calculate this quantity. This quantity here. What is this? Right? And you can quickly calculate that. A double prime by A is what? Is A double prime by A is beta. Just a minute. Let me see whether I've written as beta. Okay. Oh, A beta plus 1 times beta. Okay. right, divided by eta square. This is what I have taken. And when beta equal to -2, right? When beta equal to -2, a double prime by a is -2 by eta square. Okay? Sorry? No, beta is -2. Oh, okay, that is correct. -2 plus. Oh, no, it's 2 by eta square. There is a minus already here. Sorry, it's 2 by eta square. Correct. Okay, so what are we interested in? We need to impose initial conditions and evaluate the spectrum at late times. And I have been saying, I'm going to erase all this. I don't need this. I'll retain this picture to make a few points. So what are we interested in? We are interested in k squared, okay, to be greater than beta into beta plus 1 by eta squared, right? Okay. Now, what do we have? AH. Remember, the Hubble, sub-Hubble and super-Hubble scales correspond to K much greater than AH or K much less than AH. Now, what is AH here? Okay. AH is script H. Remember what is script H? This script H is a constant. It has a subscript. Okay. All right. What is script H? It's A prime by A. Okay. What is A prime by A here? Modulo constants. Okay. So this is like 1 over eta squared. This guy. This is okay. And A prime by A is just beta plus 1 by eta. So this is like 1 over eta. Okay. So what do we want? You want K much greater than 1 over eta. This is, what is it? Sub-Hubble regime. Okay. When the modes are here. The super-Hubble regime corresponds to K much less than 1 over eta. So these limits correspond to K eta much greater than 1. And this corresponds to K eta much less than 0. Okay. Or you say this tends to infinity and much less than 1, sorry. And this tends to 0. Is that clear? Okay. So in other words, what have I said? The sub and the super Hubble limits correspond to the domain when this is dominant than this or this is dominant than this. If this is dominant, it is the sub Hubble regime. K is large. Okay. Okay. And when this is dominant, it's the super Hubble regime when K is ignorable. Is that clear? So now, what is amazing is that do we know the solution to this in the super Hubble regime? We know to solution of this type in the super Hubble regime. We did that. We had, if you recall, we had some quantity called U subscript K describing the Bardian potential, and there was a theta, and we wrote down a solution. One solution was evident. What is one solution? Vk is proportional to A in the super Hubble regime. The other solution, you need to do a little more exercise, but I asked you to check that is indeed valid, that solution. So we know the solutions in the super Hubble regime. What is the sub-Hubble regime? Is the regime when you can completely ignore this. Do you know the solution? It's a simple harmonic oscillator. That's all. So all I'm going to do is that I know the solution in one regime. I know the solution in the other regime. I don't care what happens. I just match them blindly at Hubble exit. What is Hubble exit? When these modes leave the Hubble radius. This mode, I'm just drawing one mode so that I don't clutter the picture. Okay. Remember, this is the Hubble radius, right? Okay, this is slope of 2. This is a slope of 0 during inflation. Okay, and what happens? So this is in the sub-Hubble regime. Now, what are the two solutions that are available to me? In the sub-Hubble regime, what are the two solutions that are available to me? Okay, maybe I should write that down now. Okay, so this picture I will retain. I will erase these guys. I will keep this equation. I presume you know all these. Right? Okay. So I will write this equation again. Vk double prime plus k square minus a double prime by a, which is, I know this, beta into beta plus 1 by eta squared, Vk equal to 0. All right. Now, all it was about initial conditions. Okay. So Vk is what? I can write this as some script ak e power minus ik eta plus script vk e power ik eta. Correct? Now, what happens is that at very early times, okay, I have erased this. Remember, Rk was what? The operator Rk was what? If you recall, if you look at your notes, it was Ak, Vk or Fk, Vk by Z e power, that's it, okay, plus A minus K dagger Vk star by Z is real, so I don't have to worry about it. This was Rk. In fact, this was R vector K, if you look at your notes. Now, this is the coefficient of the annihilation operator. And the annihilation operator defines the vacuum state, okay? So I'm going to choose this, and to normalize that he was asking about, I'm going to choose my initial conditions to be 1 over root 2k. And that actually comes from the Wronskian condition, etc., etc. I don't have time to go into it, okay? But, you know, it's like quantization of scalar field. And you have solutions of the form for Vk, which is 1 over root 2k e power minus ik eta, okay? And once I choose that, it is when Ak, for this initial condition, okay, Ak equal to 0, this is my Bunch-Davies value. Okay, and I hope you have seen that K appearing there. That's equivalent to your EP that you may be familiar with. We are something like effectively massless fields that are appearing here. Okay, so we have chosen the initial condition, right? This is in the sub-Hubble regime. Okay, so in other words, I have Vk equal to 1 over root 2k e power minus ik eta in the sub-Hubble regime, right? And what am I going to do? I'm going to write the super-Hubble regime, okay, solution. I know the super-Hubble solution. Vk equal to some, okay, let me see what quantities I have introduced, okay, so that I am right, okay. So can you guess what will be the solution? It will be that script ak, I fixed that, okay, and now it's without the script a, all right. What will be the solution? What is one of the solution for Vk in the super-Hubble regime? Okay, let me write this here so that it is evident. Sub super. Ak times A, right? It's evident, right? This was A double prime by A. Okay, so Vk proportional to A is one solution when K is negligible, correct? And the other solution we had seen is, I can write this as Bka integral d eta tilde by A squared eta tilde eta, integral up to eta. Okay, that's all there is to it. Now, I have imposed the initial conditions. If I know Vk, I know in principle Vk prime at early times as well. Okay, and I hope it's clear. What is happening is that, what is the curvature scale here? During the inflationary epoch, what is the curvature scale? It's the Hubble radius. There is nothing else present, okay? You calculate the curvature and see that curvature is 1 over length square, okay? There is only one scale in the problem essentially, okay? The curvature scale is proportional to, is determined by the Hubble radius. And when you say that the wavelength is inside the Hubble radius, what do you have? You are focusing on a domain which is much smaller than the curvature scale, okay? Well inside the Hubble radius. So what essentially happens is that the modes behave like as though they are not seeing the curvature, which is like what you're doing in Minkowski spacetime. So in that domain, you have a simple solution. It's not exactly Minkowski because there is a Z that is also present here in your mode. In Minkowski, there won't be Z present. There is no scale factor. Okay, so it's not truly Minkowski in that sense, but what essentially happens is that you're focusing on a domain much smaller than the Hubble radius. And there was a question about, how do we define the vacuum state in such situation? This is the best way we can define the vacuum unambiguously. When the modes are well inside the Hubble radius, I expect a VK to behave like a positive frequency mode. Such a solution is often referred to as a positive frequency mode. The coefficient of it, the annihilation operator, allows me to define the vacuum state, and that sets my initial conditions. Okay, which means I know VK and VK prime, right? And I can, in principle, if you have a numerical code with those initial conditions, I can impose. Okay, I can evolve rather the differential equation governing V or R, whichever is convenient. Okay, now what do we have analytically? We have the solutions in the sub and the super-Hubble regime. Yes, they are not supposed to be perfectly valid close to Hubble exit. What is Hubble exit? Okay, notice the modes leave the Hubble radius once during inflation, all the modes. They have to, all observable modes have to emerge from inside the Hubble radius during inflation. As I mentioned, you need a duration of inflation that is sufficiently long so that all cosmological scales of interest emerge from inside the Hubble radius. And they emerge with those initial conditions. Okay, you can endlessly argue whether these are the initial conditions, whether the initial vacuum can be excited, etc. But those all, yes, you can assume that. You have to justify those assumptions, and you have to check whether it is consistent with the cosmological data. Okay. Anyway, coming back to the story, we study evolution from the Bunch-Davies vacuum, which means Vk at early times is given by this expression. At late times, we have a super-Hubble solution. And if I match Vk and its derivative at Hubble exit, right, I can determine Ak and Bk. That's it. Okay. I will let you do that as an exercise. And I'm just going to, what I do is that then I know Ak and Bk. This is what the function which is valid at late times, right? And then Fk is Vk by A, all right? And you will see that this will decay away. This is the decaying mode, okay? And this is the growing mode, which is actually a constant on super-Hubble scales. And if you recall my my slides from my first lecture, okay, overview lecture, you'll find that if you plot the function Fk as a function of n, what happens is that it'll oscillate something like that. And then it'll come down and settle down at some value. Okay, and somewhere around this point is where Hubble exit will arise. This is sub-Hubble behavior, okay, and this is super-Hubble behavior. And when it is sub-Hubble, it oscillates. Okay, if you plot mod Fk as a function of n, mod Fk as a function of n, it's a positive quantity. So you'll find that it comes down and settles down after Hubble exits somewhere here like this. If you zoom in, there will be tiny oscillations. I'm just plotting its amplitude. It comes down and settles down. Okay. So what happens is that on these super-Hubble scales, soon after Hubble exit, the modes amplitude freeze, and that's in the super-Hubble limit, so to say, you can evaluate the spectrum. So what do we need? We need the okay. So okay. In fact, as I said, I'm just going to even ignore this. Okay. So I can match this and this at Hubble exit, okay? And you can immediately determine what is A, capital A, and you can write the power spectrum. Okay, so what you find is that Ak is 1 over root 2k e power ik eta e. I will tell you what that eta e is. Some A naught. I'm taking into all the expressions here. Remember, the A contained the script H1, okay? And it is eta E power minus beta plus 1. What is eta E? Eta E is the time of Hubble exit, okay? Eta E, okay, happens to be minus root beta plus 1 by k. That's not surprising, right? This is when this is equal to this. Yeah? Okay. So remember the power spectrum, all right? And you can calculate the power spectrum, and you obtain, after a lot of algebra, you can arrive at, not complicated algebra, simple algebra. So what does it mean? You know Vk, you know A, and you're evaluating the spectrum at late times, okay? And you find that the spectrum can be written in this form. This is the case of scalars. All right. Okay. This is the spectrum. And what happens when beta equal to -2? What was beta equal to -2? What did we refer to beta equal to -2? Take a look at your notes. It's the de Sitter limit. T power q, q being very large. Q being very large means A of t is e power ht. Okay. All right. So in the de Sitter limit, there is an issue with discussing the de Sitter limit. I will mention in a matter of minutes. In the limit, in the de Sitter limit, beta is equal to -2. The spectrum is, there is a term that's often used, I'm sure you know, scale invariant. It's scale free, completely, it's scale invariant. It's an amplitude that's determined by this parameter, whose amplitude is determined by this parameter. When beta is very close to -2, it's what we will refer to as slow roll inflation. You have a nearly scale invariant spectrum. Okay, but there is a problem in the de Sitter limit. Okay, remember what we have done in carrying out this exercise. We said this is a phi dot by h, correct? I mean, z is a phi dot by h. In power law inflation, phi dot was proportional to 1 over t, okay, and h was proportional to 1 over t, and we said z equal to a. But remember, what was de Sitter? It corresponded to a cosmological constant, right? We discussed this. And if you have a is e power ht, correct? V is 0. I'm sorry, V is constant, V being the potential. V of phi is a constant, and phi dot is 0. And that gives me trouble. So the de Sitter limit is actually pathological. You need to be careful. Okay. But yes, you are able to reproduce the right result. But I cannot define Z in the de Sitter limit. Okay. So no one considers the de Sitter limit for this reason. People don't consider the de Sitter limit for the scalar perturbations. I will come to the tensor perturbation within a matter of in some time. Okay. So now what we need to do is that this is the spectrum in power law inflation. We will need to determine the spectrum in slow roll inflation. Okay. And you don't want to do it model by model. You want to do it in a model independent fashion. And we will do that. We will introduce what are known as slow roll parameters. Okay. A hierarchy of slow roll parameters. I introduced two slow roll parameters. I refer to them as potential slow roll parameters. There was epsilon v and eta v, which were essentially dimensionless quantities involving the first derivative and the second derivative of the potential. And we said if those quantities are small, I can determine in a potential where slow roll inflation will occur. Okay. But we want a more precise definition of the slow roll parameter, one of which I introduced. I said epsilon 1 is minus h dot by h squared. And I said this quantity, if it is less than 1, corresponds to a double dot greater than 0. I would urge you to show that. Okay, h is a dot by a. So calculate epsilon 1 and show that epsilon 1 being less than 1 corresponds to a double dot by a greater than 0. Okay, using from the definition of the first slow roll parameter, we will define a hierarchy of slow roll parameters. And what we will do is that this quantity was z double prime by z. We will write the z double prime by z in terms of the slow roll parameters. And we will see that the solution will be very similar. And this index that we have obtained beta, okay, in the context of power law inflation, will be replaced by some quantity involving the slow roll parameters. There will be a set of slow roll parameters that will appear here. Okay, so the index can be written completely in terms of the slow roll parameters. Okay, and if I know the value of the index from observations, from CMB observations, then I can constrain what the slow roll parameters are, and which in turn allows me to constrain what's the nature of the potentials. Okay, so I notice that I've already crossed my time. So I will just tell you what the scope of the next lecture is going to be, and so that I can sort of change gears in order to make good progress. Whatever we have done until now, we need to repeat for the case of tensor perturbations. Okay, so I will just make a time permitting, I'll make a brief remark about vector perturbations. I will write down the equation governing the vector perturbations. Okay, I will work in a particular gauge. And if there are no sources, which is true in the context of inflation, right? There is only a delta phi, there are no vector sources. You can show the vector perturbations will not be present, okay? Will not be generated at all. Not so with the tensor perturbations. Remember, in the case of tensor perturbation, there were no additional gauges left. We had fixed, there was no other additional degrees of freedom. There were only 2 degrees of freedom, which corresponded to the 2 polarizations of the gravitational waves, okay? So what we need to do is that with the Hij that we had introduced in the metric, we need to calculate the perturbed Einstein tensor, okay? And here, in the case of scalars, we had a source. We had a scalar field now during inflation, or at later times, we have fluids acting as a source. In the case of tensors, we will have no sources. Well, you can include sources. They can be magnetic fields, neutrinos, they can. But for simplicity, we assume that there will be no sources. And what you will find is that the Hij that we introduce will satisfy an equation very much similar to the curvature perturbation that we had. It's not difficult to arrive at. It's fairly straightforward. Once you calculate the perturbed Einstein tensor. And then you can define a Mukhanov-Sasaki variable, and you will find that it will satisfy an equation very similar to this, okay? It is just that, in power law, it will be the same, power law inflation, but in slow roll inflation, scalars and tensors, this quantity here, okay, that appears over 1 over eta squared will be different for the case of scalars and tensors. So they will have different what are known as spectral indices. But the calculation of the spectrum is essentially in the same fashion, okay? And we will determine what are the quantities we need to determine. We need to determine, if you recall my original lecture, for simplicity, cosmologists write the tensor and scalar spectra of a power law form, and they introduce an amplitude for scalars, a spectral index for scalars, and similarly an amplitude for tensors and a spectral index for tensors. And we would like to know what they are in the context of slow roll inflation. And that will be the scope of my next lecture. I am now fully a lecture behind, but I will proceed as it goes. Thank you. We'll meet after lunch.